Hello everyone, and welcome to the Dry Ice Puck on a Ramp post-lab. Now, if you are watching this post-lab, you should have already done the pivot, answered all the questions inside, gotten the position time data from the dry ice puck going down the ramp part of the video. You should have put all that data onto your lab sheet, gone into graphical analysis and graphed it and linearized it, answered all the questions on the lab sheet all the way up to making a math model. Right? And at one point that included even putting your slope into a Google form as a check, right? So that I can gather them all up and see them all, right? But it also gives you kind of a check as to whether you're getting a number that's fairly close to what I think it should be, right? Based on me taking data in that lab. You should have that lab sheet out in front of you right now so that you can take notes on it, make adjustments to what you've written, add things to it, take notes, whatever you need, right? But have that lab sheet out as you're going through this post-lab. So, you took data on position versus time for the dry ice puck going down the ramp, and when you made a graph of that, you did not get a linear graph, which again shouldn't have been too much of a shock because we got linear position time graphs for constant velocity. And this dry ice puck was definitely speeding up as it went down the hill. And so we got a graph that looked like this. Everybody remembers that from the area of a circle lab. This is called a top opening parabola. Right? Top opening because the opening is at the top. Now it is a parabola, although we're only seeing half of the parabola. Technically the other half is over here, but that's in negative times, which doesn't really have a physical meaning for us. So we're seeing the part of the function that actually applies to the real world. Right? As we often do in here. This isn't math class. Right? This is physics, and so we can only deal with things that actually exist in nature. So you got this position time graph. So you had to linearize it, and that means you needed to do something to the time. So hopefully you thought back to the labs we've done in the past, in particular the area of a circle lab, where in order to linearize a top opening parabola, we had to square the x value. So in this case, if we graph position and time squared, notice in seconds squared, if you square the variable, you have to square the units. And that should have given you a linear graph. And not only a linear graph, but one that, as you calculated later on in the sheet, essentially went through 0, 0. And when you graph two variables, and the resulting graph is linear and goes through 0, 0, what does that tell you about the two variables, about the relationship between those variables? It tells you that they're proportional. But not position and time, because that did not give you a linear graph that contains 0, 0. It's position and time squared. Right? We're gonna look at that here in a moment and look at the data and everything and see how that works. Okay? But its position is proportional to time squared. Right? Is how we would read these symbols. Position is proportional to time squared, not time. Now, let's look back at our data. Hopefully your data looks somewhat like this. This is kind of what I measured, or roughly what you probably got in the lab. So let's take a look here at the 0.2 second time when it was at about a position of roughly 7-ish, right? So let's double that time. And instead of 0.2 seconds, let's double it to 0.4 seconds. And notice, the position did not double. 7 did not double to 28. In fact, how many times greater is 28 than 7? Yeah, it's 4 times greater. See that? Your time doubled, 0.2 to 0.4, but your position went up by 2 squared, or 4. If we triple the time from 0.2 to 0.6, it doesn't go up by 3 times, which would only be 21. Right? It goes up to basically 9 times as much. Now I know this isn't exactly 9 times, but there's error in this lab, right? Depends how well you can measure everything, and even with a high speed, good quality video, right, we still might get a little bit of error creeps in here, okay, just from making these measurements, whether or not there's friction and stuff like that, right? But it goes from 7 to 64, which is basically 9 times as much. Triple the time, 9 times the position. Quadruple the time from 2 to 0.8, and yeah, we get basically 16 times the position. 7 times 16 is not quite 100 and 114. It's like 112, right? But it's still basically, right, pretty close to being 16 times. So that's what I mean when I say position is proportional to time squared. And that makes all the difference in the world between this kind of motion, which we will eventually name, and constant velocity motion when the position was only proportional to the time. You let it go, you let the toy car go for twice as long, it went twice as far. 3 times as long, 3 times as far. Not so easy here. But hopefully you can see it in your data as well as in my data. But we did linearize. And since we have a linear graph that goes through a linear line that goes through 0, 0, linear line, that's redundant, right? Linear function that goes through 0, 0, we can make a y equals mx plus b math model. Except we're not going to use y, m, x, or b, right? We're going to use real numbers, real quantities, and real symbols here. So what is our y in this case? That's what we graph on the vertical axis. Well, it's actually position, or x. Again, this is why I tend to say horizontal and vertical axis, because here we're graphing x on the, what in math class is traditionally called the y-axis, and that's confusing. So our vertical axis here is position, horizontal position basically, so x, or parallel to the incline, if you will. And that's going to equal the slope. I figure the slope is about 178. Right? When you put your slope into the Google form, right? If it took it and said everything was good, then you were within 5%, give or take, of this. I think is the range that I allowed before I said, you better go back and check something. So everybody got a slope of roughly 178-ish. Again, if yours is a little different, that's okay. Write yours in. Okay, it's what you got out of the lab. There's going to be some differences, which are okay, because of error in measuring and that kind of thing. Now, we do need to put units on it if we ever have a hope of understanding what it means. Slopes are, of course, rise over run. So the units of rise are centimeters. The units of run, not seconds, that's not the linearized graph, right? Seconds squared. Okay, so it's roughly 178, 180 to 2 sig figs, centimeters per second squared. We'll talk more later about what that means, but it's going to actually take us another day or two to get there. So what's the x variable? That's what we graph on the horizontal axis. Well, it's not time. That's not the linearized graph. It's time squared. Remember, we're creating a math model not just of this graph, but actually the math model of that graph as well. And squaring the time is what gives us a parabola on that graph. The y-intercept, however, both logically and by the 5% rule, if you put your 0 line right on the right edge of the puck, right, and started it at the frame that it talked about in the pivot, which was right as the wire was cut, right, then you should have had a true 0, 0 point. Which means what in this case? At 0 time, you had 0 position. That should be centimeters, not meters. Sorry, I switched it everywhere else but there. Right? So that should be centimeters. So every 0 seconds, the position is 0 centimeters. Close as we could in this lab, we tried to have that nice 0, 0 point. And of course, you don't have to add 0, so there's our math model. Or hopefully you have something fairly close to that. Now, as I said a moment ago, right, usually we try to look at slopes and see what they mean. I'm not going to ask you to try to interpret this one because we really don't have enough physics yet. We need to develop some further ideas, and then we're going to come back and be able to put in what the slope is. Okay? So what I suggest you do is go on your lab sheet. The very last question on the back page is make a math model, right? So you should have a math model that looks something like this. Write slope equals, and maybe put a line there. And we're going to come back and write in what the slope is. Okay, so put that on your lab sheet. I'll ask you to pull it back out in a couple of days here, and we will write in what that slope actually is supposed to be. And so at this point, that's what we need to know about the position and the time for the dry ice puck going down the ramp. It's a predictable pattern. Right? Position is proportional to time squared, but it is more complex than constant velocity. Right? It's still special because it's position proportional to time squared, not something funkier and more complex, which can certainly exist, but it's more complex than constant velocity. So we're going to have to use some different techniques in order to understand what's happening with, say, the velocity and other things as we go throughout the unit. So hopefully you've completed your lab sheet, completed the pivot, right? You can upload your lab sheet now with all correct answers on it and everything, right? So that you can get credit for it.